We are going to look at chemical reactions and learn how to balance them in this video. So we already know a little bit about chemical reactions from earlier in the course. Chemical reactions are when atoms are rearranged to form a different substance. Essentially, it's a chemical change taking place. But remember, one atom cannot become another atom. So in order for a reaction to take place, atoms that you already have there are just rearranged to form new substances. So if you look up here at this example, okay, if you have H2 reacting with Cl2 to form hydrochloric acid, okay, notice the H's and the Cl's are still there in the final products. It's just that they have rearranged themselves, so they're no longer H2, they're no longer Cl2, they have formed HCl. All right, so they formed a new substance, but the atoms were there in the beginning. All right, but the new substance would have different properties. It's no longer hydrogen, it's no longer chlorine once it forms the HCl. Okay, so you can't just create or destroy atoms here. You can only rearrange them in a chemical reaction. This is just a little refresher about some of the indicators of a chemical reaction. Remember, if you would see like a temperature change or a color change, or gas forming, maybe an odor change, light being given off, maybe sound, or even a precipitate forming when you mix two liquids. These are indicators of a possible chemical reaction. Remember, if you didn't get a new substance forming, even if you have all the indicators in the world, it's not going to be a chemical reaction. So you need a new substance to form in order for it to be a chemical reaction, but sometimes these indicators will key you in on when a reaction took place. A chemical equation here shows us a chemical reaction taking place. So we always have the reactants on the left side. That's always what we start with in the reaction. And then the products are always what form. The products are always on the right side. So the reactants always become the products in a chemical reaction. So this example here of photosynthesis is really good because it clearly shows you here on the left side the reactants, the water, the carbon dioxide, and the sunlight all going in. And then you can see the products, the glucose and the oxygen that form. Okay, so this is a good representation of a chemical reaction. These are some of the symbols that you could see in these chemical equations. Some of them are used all the time, so they're more common. Other ones you have to kind of remember. So you can see the plus sign, which would separate the reactants or the products. The arrow is what separates, the reactants from the products from the left from the right. This symbol here indicates that a reaction is reversible, meaning it could go forward or reverse. Okay, that's kind of an equilibrium thing they would talk about in AP. These little symbols here, the S, the G, and the L in parentheses, that just tells you what state of matter the substance is in. So if something in the reaction is a solid, you would put after it in parentheses, you'd put the S, okay? And that would indicate that you're reacting the substance in the solid form. G is gas, L is liquid. We don't really hold you accountable too much for this in this unit. It's kind of more important when we get to solutions and needing to pay attention to the solids and the liquids and stuff in that unit, but just be aware of them. This one's kind of interesting. If you see AQ in parentheses after a substance, that means it's been dissolved in water or the substance dissolves in water. Okay, so that's kind of important. The triangle here, that indicates that heat is kind of applied here to a reaction. So how you would see that is in a reaction over the arrow. When you're writing a reaction, you'll have your reactants, okay, and your products here written. But what you would do is you would see the triangle over the arrow, and that would indicate that heat is involved or heat is needed here to make this happen. Okay, and then you also have catalyst. You might remember catalyst from biology. This is just something that speeds up a reaction, but it's not a reactant and it's not a product. So same deal, the catalyst would just be written over the arrow. So if you see a reaction, okay, and you have something like yeast over the arrow, that would indicate that yeast is a catalyst. It's not a reactant, it's not a product, it's just there to speed up the reaction. Okay, so that's a common catalyst. There's other catalysts as well. We sometimes can see manganese dioxide as a catalyst. Sometimes platinum might be used as a catalyst. Okay, so the key is when the substance is written over the arrow, it's indicating that it's just there to speed up the reaction. So some general rules here for writing reactions before we actually jump in to doing this. The reactants always must be on the left side. The products must always be on the right. You do have to write the correct formulas here in the symbols. So you might need to use some of those naming or formula rules from nomenclature. So you might have to follow symbols, charges, crisscross for ionic, so on and so forth. And we do use an arrow to separate the reactants from the products. So if you look at this example here, again, you can see that I gave you the state for each of the substances. And like I said, usually you're not accountable for that, but this would basically just be saying that solid copper is reacting with chlorine gas and it's going to form copper 2 chloride, and that would be a solid. Okay, so you can see the arrow here separating the reactants and the products. You know that the left side would be your reactants and the right side would be your product. All right, but typically we don't hold you accountable for knowing whether it's a solid, liquid, or gas, but you do have to pay attention to the actual equations and formulas here. So we're going to do some quick practice here, writing some skeleton equations. This is going to be, a skeleton equation because we're not going to worry about balancing it yet because we haven't learned how to do that. So we're just getting used to writing out an equation and practicing this. So the first one says hydrogen and bromine are forming hydrobromic acid. So it looks like we have an acid here. So we will have to pay attention to our acid naming rules when we're doing this one. But we're just going to start with our reactants and then work our way to our products. So the first thing I see is hydrogen. So you got to be careful here. You can't just write H, because if you remember back to bonding, okay, hydrogen cannot exist by himself. Hydrogen is one of those diatomics. So hydrogen is actually H2. All right, so you have to be careful of that. Anytime you have one of those diatomics that were on the list, you can't just write the element by itself. This would be like Cl2, F2, O2, N2, and also bromine, Br2. So hydrogen is reacting with bromine, but he's not just Br, he's Br2. So anytime you have one of these guys by themselves, they have to be in the diatomic form. All right, so just be careful of that. We don't need to pay attention to the G. All right, we're not worried about the state here. All right, but this is saying that these guys are going to form hydrobromic acid. So if you remember your acid naming rules, this one is hydro root ic. Okay, so that would be rule 1. This hydrogen is going to be attached to something that ends in "ide." So if I write this over here real quick, I know I'm going to have hydrogen because it's an acid. So I immediately write H plus. And then because we said it's going to be something that ends in "ide," the root is brom, so it's going to be bromide. That's just Br. And bromine is 1 minus when you look it up on the table. So when I crisscross, hydrobromic acid is just HBr. Okay, and if you're looking at this closely, you'll see that this is not balanced, okay? The number of hydrogens don't equal the number of hydrogens on both sides. Same thing for the bromine, but we're just doing a skeleton equation here. So that would be the basic skeleton equation for that reaction. So let's try another one here. It says potassium chlorate breaks down into potassium chloride and oxygen, all right? So I'm going to start with my reactants and then work my way to the products here. The first one I have is potassium chlorate. All right. How are you going to get the formula for potassium chlorate? This requires you to look at this and know, oh, look, this is a metal, non-metal. This is ionic. In order to write the formula for ionic, I have to do symbols, charges, crisscross. Anytime you see a compound here that's ionic, you have to do symbols, charges, crisscross to get the formula. So you can kind of write this off to the side, but potassium chlorate, potassium is going to be K. All right, chlorate is going to be ClO3. All right, that's a polyatomic. You need to know your polyatomics. So now we did the symbols. So now we do charges. Potassium, when you look it up on the table, is going to be plus. Chlorate is 1 minus. So when I crisscross, potassium chlorate is just KClO3. All right, now this one's saying that breaks down into potassium chloride and oxygen. So potassium chloride, same deal here. It's an ionic. You're going to have to do symbols, charges, crisscross. So potassium is K. Chloride is just Cl. All right, potassium charge is plus, chlorine is minus. So I wrote the symbols, I wrote the charges. When I crisscross, it's just KCl plus oxygen. Oxygen is one of those diatomics, so it's got to be O2. So watch your diatomics, watch your ionics. You got to follow the proper rules here for doing these things. Okay, so these were just some examples of some skeleton equations. So now we want to look at actually balancing chemical equations. And basically the reasons why the equations need to be balanced is because we cannot break the law of conservation of matter. You can't end with more atoms of one substance than you started with, because then you would have essentially created matter here. Okay, so you have to have the number of the atoms that you're starting with equal to the number of the atoms for that particular element that you're ending with. Okay, so you can have different amounts of, say, hydrogen and oxygen, but the key is the amount of oxygen must match the amount of oxygen in the reactants and products, and the amount of hydrogen must match, in the reactants and the products. Okay, and the only thing you're allowed to do here to balance chemical equations is use coefficients. All right, and I'll show you what this looks like and I'll show you what this means. But basically, you're only allowed to put numbers in front of things. You're not allowed to add numbers in between or add subscripts or anything like that. All right, so that's what we're going to look at here as we balance equations. So this is just showing you the difference here between coefficients and subscripts. Subscripts here are the small sunken down numbers, all right, in formulas. They are literally telling you how many atoms you have of each. So for example here, there's 2 atoms of oxygen, there's 2 atoms of hydrogen. All right, over here, when there is no number, we assume there's 1. All right, so there would just be 1 atom of oxygen here, 2 atoms of hydrogen. Coefficients are the big numbers that go in front of an equation. All right, these are essentially telling you like how many molecules you have. So in this case, when we put a 2 in front of this, we now have 2 whole molecules of H2. This one, there's no number in front, so there's just 1 molecule of O2. And here, with the 2 in front, there's 2 molecules of water. Okay, so the only thing you're allowed to do to balance equations are put coefficients, the big numbers, in front of things. That's all you're allowed to do. You're not allowed to change subscripts in order to balance things. And it's important that once you put these coefficients in front, they essentially multiply through. So by putting this 2 in front of the H2, we now have a total of 4 atoms of hydrogen, 2 times 2. Okay, here there's no number in front, so it's like 1. There's still 2 atoms of oxygen. And here with the 2 in front, there's now 4 atoms of hydrogen, but 2 atoms of oxygen. Okay, so pay attention to the difference between coefficients and subscripts. So I just want you to see this example here. If you look at this, okay, if you could take carbon and react it with oxygen, O2, if the conditions are right, sometimes that'll form CO2. So if you look at this, I try to give you, look, the carbon's in blue, the oxygens are in red. If you look at this, you can clearly see this is balanced, okay? You have 1 blue on the left side, on the reactant side. You have 1 blue atom on the product side. You have 2 red oxygen atoms on the left, and you have 2 red oxygens on the right. So this would be balanced, okay? The blues don't have to equal the reds. It's just that however many blue you're starting with, that's how many blue you have to end with, okay? Same deal for the oxygens in red. So this would be balanced. So kind of a similar reaction here. If you take carbon reacting with O2, under some conditions, okay, you get carbon monoxide, not carbon dioxide. Depending on the conditions here, you might not form carbon dioxide, okay? Carbon monoxide is what forms, and that's just the way it goes, okay? So you can clearly see in this one, this would not be balanced, okay? I need more oxygen. I need more red on the right, on the product side, okay? I have 1 blue on each side, but the red doesn't match up. Okay, so you have to think about what could I do now in order to make this work? Well, since you need more oxygen on the product side, the only thing you can do is form more carbon monoxide. That's the only way you can get more oxygen. If the only thing that forms is carbon monoxide, you can't just add an O, okay? Because that's not what forms. So the only way I can get more red on the right is by adding another molecule of carbon monoxide. Now the reds match up. I have 2 red on the left on the reactant, and now I have 2 red on the product side. But the carbons don't match anymore. Okay, so now you can see I have 2 carbons on the product side, but only 1 on the reactant side. So I got to make that work. So when this equation is balanced, what you'll see happens is you actually have to start with 2 carbon atoms reacting with 1 O2, okay, in order to form 2 carbon monoxide. That's the only way this reaction would be balanced. If you didn't have 2 carbon atoms to start this reaction, it would not take place, okay? So if this is what forms, the only way you can get more of what you need on the product side is by forming more of that product. Okay, so notice if you count things up here, this equation is now balanced. Some things to watch out here for when you're balancing. You can never change a subscript to balance an equation. All right. You can't just say, well, oh, I need more oxygen in water, so I'm just going to make it H2O2. You just made water become hydrogen peroxide. You can't just add a subscript. Okay. You can't just say, well, I need to take my coefficient and put it in the middle of a formula. So NaCl becomes Na2Cl. Nope. You just totally change the formula. All right. The only thing you're allowed to do here to balance a reaction is put coefficients in front of things, okay? So you got to be careful with that. You can't just change subscripts. You can't just throw things in the middle of formulas. The only thing you're allowed to do is put numbers in front of an entire substance. So at one point, I used to go through all these different rules for balancing, and really, there's one rule that I'll show you here. The best rule for balancing is just making this what we call reactants products table. Okay, it looks something like this. You have your reactants here on the left side, you have your products on the right, and you put your substances here in the middle. And this can even get bigger and get more rows depending on the reaction. But literally, you have your substances in the center, and you'll just start counting things up on each side. And this will be a nice way for you to see if an equation is balanced. Okay, so I think just doing some of these and practicing will help you balance them and learn how to do this. So first example we're going to do here, we have H2 reacting with O2, all right, forming water. All right, so sometimes these reactions are balanced from the beginning, but I can clearly see here in this one, I have 2 oxygen on the left, but only 1 on the right, so I know this is not balanced. So I'm going to make my reactants products table here to start this. So R goes on the left, products go on the right. All right, and then I start putting my elements in the center. All right, so literally when you do this, you just start on your reactants and you just move left to right and you identify any elements you see. All right, so the first element I see here on the left side of the equation is H, so I'll put that in the center. Then I'll put a line for another row. The next element I see left to right is O. All right, and then I hit my arrow, and then notice the elements are always going to repeat the exact same on the product side because they have to be balanced. So once you hit your arrow, you're done. So there's only H's and O's here in this reaction. So now I just count up, okay? So I look on the reactant side, I say, okay, how many hydrogen on the left side? Well, if you notice, there's just 2, all right? Same thing with the oxygen. How many on the left side? There's 2. Okay, so on the product side, how many hydrogen? Well, there's 2. And then oxygen has no number, so there's just 1. If this was balanced, okay, the number of each element would match for each row. So notice the hydrogens match, there's 2 and 2, but the oxygens 2 and 1, they don't match, okay, across. So I have to make the oxygens work. So the only thing I'm allowed to do here is add numbers in front. I'm allowed to add coefficients, all right? So I know I need another oxygen on the right side, on my product side. So the only thing I'm allowed to do is basically create more water. So I'm going to put a 2 in front here, all right? But once you do that, you need to reflect those changes in your table. By putting a 2 in front, all right, there's now going to be 2 oxygen on the right side. But it inadvertently changes my hydrogen. Sometimes this happens. In order to make the oxygen work, I now changed my hydrogen. There's now 2 times 2 hydrogen, which is now 4. All right, so now I have to go to the left side and fix the hydrogen. The oxygens are all balanced now. So when I go over here to the left side, say, okay, I need this to be 4 now on the left. So the only thing I'm allowed to do is put numbers in front. I'll put a 2 in front of the hydrogen. 2 times 2 is 4. Okay? This oxygen here has no number in front. That 2 does not affect him. Okay? He only affects the hydrogen. So this is now balanced. Right? So when you were done with this, okay, this would be the balanced equation. All right? That's what you would see in order for it to be balanced. So if we just get rid of kind of these lines, okay, that's what you would write for the balanced equation here, all right, and that would be the correct balanced equation for this reaction. So now we're going to try another example here. We're going to make it a little bit more fun, but before we do this example, I need to point something out that's very important. All right. So basically, if there's a polyatomic ion present in a reaction, and that polyatomic ion is present on both sides of the equation, okay, that's important. It needs to be in the exact same form on both sides of the equation. You can actually group it together in your table. So for example, in this reaction, NO3 is the polyatomic nitrate, all right? And the NO3 is here again on the other side. So when I'm doing my table, I can put NO3 in the table as one. I don't have to split it into N's and O's, okay? If this was NO2 on this side, well then that's not the same. NO3 is not the same as NO2. So I would have to split it up into N's and O's. You're more than welcome to split it up and do Ag, N, O, and Cu for your table, but it makes it a little bit easier to group the polyatomic ion together. Sometimes you have no choice. You have to split it up, all right? But a lot of the times it does make your life a little bit easier by grouping it together. All right, so now we're going to try this reaction here. So we're going to make our reactants products table. Very important to understand here that you won't need to do a reactants products table for all of these eventually. I kind of show it on the first day. We get used to doing it. It's kind of a tool that you can use in case you stumble upon a reaction that you're not quite sure how to balance. Definitely can come in handy. Some people like to do it for all reactions. But usually here for the first day, I say get used to using it, know how to do it, and then eventually you kind of can only use it if you need to. So we're going to identify our elements here we see moving left to right across our reactants. So the first element I see is Ag. So I write that in the center. And then remember here we got the NO3 next. Because it's the same on both sides of the equation, I can group it together because it's a polyatomic. All right, but it has to be the same on both sides of the equation. All right, and then the next element I see here is Cu. All right, so then that's it. Those elements would repeat on the product side here. So now I'm just counting up. So for Ag on the left, there's just one. There's one whole NO3, and then there's one Cu. On the product side, all right, there's going to be just one Ag. There's going to be two of the NO3, and then there's just one Cu. Okay, so I can clearly see here my Ags are fine, my Cus are fine, they're balanced. It's the NO3 that doesn't match up, 1 and 2. All right, so I'm going to have to fix that here. So the only thing you're allowed to do is put numbers in front of things, coefficients. So if I need more NO3 on the left, I can only add a number in front of the entire AgNO3. It's going to mess with the amount of Ag, but it's going to happen. So now I need to reflect these changes in my table. So now I have 2 Ag on the left and 2 NO3 by putting that 2 in front. So now I need to fix my silvers on the right side. So I need more silver. So the only thing I can do is put numbers in front. So I'm going to put a 2 in front. So now I have 2 silver on the right. Now everything matches up. That would be balanced. Okay? So we're going to try a few more examples here. You're more than welcome to pause the video, try this on your own. Make sure you can do it. But we're going to do reactants products tables here for these, just so we get used to doing these. And there might be some other little things I want to point out in some of these examples as well. So this first one here, we have Mg reacting with N2 to form Mg3N2. Okay, so we'll do our reactants products table. So the first element I see moving left to right is Mg. The next element I see is N, and those are the only elements. So now when I count Mg here, there's just one on the left, there's 2 N's, there's 3 Mg on the product side, and 2 N's. All right, so the Mg here is the problem. It doesn't match up. The only thing you're allowed to do is put coefficients in front of things. So I need there to be 3 Mg on the reactant side, so I put a 3 in front. That changes the Mg, and that's all you need to do. This one would now be balanced. In order for this reaction to occur, you'd have to have 3 Mg reacting with N2 to form the Mg3 N2. Okay, so that would make this reaction balanced now. Another example here, we're going to try this one. We have P reacting with O2, forming P4O10. All right, so let's go through, do our reactants products table. First element I see left to right moving across my reactants is phosphorus. and then oxygen, and those are the only two elements I have here. So when I count these up, I have 1 phosphorus on the left, I have 2 oxygen, I have 4 phosphorus on the right, and 10 oxygen. So notice in this one, both of them don't work, okay? The phosphorus is not matching up across the row, neither is the oxygen, okay? Sometimes that happens, so you just need to fix them, pick one, fix them, and, make it work. So I'm going to start with the phosphorus here. I need there to be 4 on the left, so the only thing I can do is put coefficients in front. I'll make a 4 in front of the phosphorus. That'll change the phosphorus here on the reactant side to be 4. But now I need there to be 10, okay, oxygen on the left here. So the only way I'm going to get 10 is by putting a 5 in front. 5 times 2 gives me 10, okay? Be careful. Sometimes people see that and say, oh, I need 8 more on the left. So they put a 4 in front. Well, 4 times 2 only gives you 8 total. You need a total of 10 on the left side, all right? So now that would be balanced. That's the only way this equation would work, and it would not break the law of conservation of matter. So the last example here, and I just want to point out something interesting. If you notice, this one here is written as HOH. All right, that looks a little weird, but I just want you to see that because basically HOH here is just another way to write H2O. All right. If you ever have H2O in a reaction, you are allowed to write it as HOH, especially if it makes your balancing easier. For example, by writing this water as HOH, you have an OH now on the left and an OH on the right. That's a polyatomic. That's the polyatomic hydroxide. So you can group it together here in your table and make your life a little bit easier. All right. So I will tell you, there are some times when grouping them together actually doesn't make it work and you need to split it up. For example, if you had like an oxygen in every single substance here, okay, so if there was oxygen here, here, and here, best bet would be just to split it, okay? But we don't have that, so we're just gonna group this together in our table when we do this. So we have our reactants products table. First element I see left to right would be Na. Then I see H. And then I have that OH, which is the same on both sides. Just remember, when you're totaling this up, the H's by themselves are not going to be included with the OH's. They're different here. So when we count here, we have one Na on the left, we have one H, we have one OH. When we do the right side, I have two H's, I have one Na, and I have one OH. So the problem here is my H's. So the only thing I can do is put coefficients in front. So by putting a 2 in front here on the left, I now have 2 hydrogen, but it changes my OH's to 2. All right, so now I got to go fix that on the right side. I need there to be 2 OH's on the right, so I put a 2 in front of the NaOH. Now I have my 2 OH's, but it made my NA's become 2 as well. So now I need to fix the Na on the left, okay? Put a 2 in front of it, and then boom, this would be balanced, okay? So it looks like you put a 2 in front of 3 of the things, but you didn't put any number in front of this one. Just an FYI, if you ever notice that you put a number in front of everything, be careful. Make sure you didn't miss the simplest form of the equation. For example, if you put a 4 here, a 4 here, a 2 in front of this one, and a 4 here, I guarantee you the numbers would work. It would look like it's balanced, but you actually missed the simplest form because all of those get divided by 2 to give you the balanced equation that we came up with. So be careful with that. If you miss the simplest form and overshoot it, you do get it wrong, even though the numbers work. Okay, so just be careful. Anytime you put a number in front of everything, make sure you didn't miss the simplest form of the equation.